Okay, so lecture 9. I didn't give you any homework over the weekend because you were going to look at the data from our survey and come back with some expert analysis. But I'll give you a homework problem set tonight. That will be a week from today. So today we're moving off of demand for the next 2 to 3 lectures to the Econ 1 for production and costs. And that's chapter 8 and 9 in the book. I definitely think it's a little limited. Something's going on here. Maybe I'll plug it in. I think that the textbook that we have is very succinct and concise. And the other textbooks that I put up on the homepage of eCourses, you could look at if you wanted just like a more Econ 1 review of these issues. And sometimes it's good to see things in a few different ways. Same graph, same term, same terminology. So today we'll be going through isoquants and isocosts, starting to think about what's behind production. And at the end, we'll tease into total cost, average cost, and we'll do those next time. So here's our data from last time that you guys all analyzed and figured out what the mean was. These are people voting on a referendum on whether they would pay a certain amount of money for an escort ship program in Prince William Sound. Just one way we could think about it. Let's see, how come it's like just a tiny bit off? We could try and think up a mean here. So a few people here vote of the total said that they didn't want to spend any money on the program. And then, so that would be $0 as a vote times like 5 people. And then we have this many people here. We could label these A, and this would be B. So this is between 55 and 65. Let's say we have 10 people here said they would only pay $10. Then we have this many people, which is between 55 and 25. So this is 30 people said that they would pay $30. And then we have something like 24 people here or something like that said that they would pay the big number of $60. Right? So we could add those numbers up. We could divide by the total number of people in our sample population and come out with an average payment that people would be willing to pay, which I don't know what it's going to be. It's going to be just more than 30, right? It's going to be like $35 is our sample average from our survey. As I talked about in the actual doing this, there's a whole bunch of different assumptions on what sort of statistical distribution you think this is, a cumulative distribution that gets the population. So how you model that distribution will change what the mean is. In the consultants working on the side of the state of Alaska for the court case, the number could vary based on what your statistical distribution was. And then say we have some number that comes out of this, like $35, for example. We could then take this number and say we did a statistically random sample of people of a certain population, and we want to multiply this average willingness to pay over a whole population size. So if we did this for 69 undergraduates at UC Berkeley, we could multiply this $35 times the population of UC Berkeley, or in the case of the actual survey, they did 1,000 random samples, and they multiplied the number they got times the population of the entire United States to come up with a number for what the value was. If you don't want to look at the statistical distribution, you could just say, where did you get half of the population? In this question of, if you want 51% to vote for a referendum, where did you get 51% of the population? Another way to think about it. And just one other thing to think about. So that in this graph, we have number of people, and our payment is going this way. But if we want to think about this in terms of demand curves, we could flip it on its side. So now we have an axis where this is the payment on our vertical axis. This is a quantity of people that were willing to pay that payment. So this gets us what we think of like a demand curve. It's important to think about this sometimes where this is the way the data is going to come out first, but But if we want to think about how to get it into demand curve, we need to invert the data so that we have dollars on the vertical axis and quantity on the horizontal axis. Okay, so moving into firms and production. I don't know why I keep chopping my thing up. So we're going to talk about techniques for production, technology for production. We're going to go through and learn to how to graph isoquants, and then we're going to start to graph cost curves. As I said, look at this lecture's on chapter 8 in the book, but definitely check out the other micro texts or the Khan Academy to supplement if it seems confusing. All right, so let's go through some definitions, how we're going to think about things in our mathematical abstractions. We're going to say that output is a quantity Q, and we have some sort of production function. This production function takes our inputs x and turns them into units of output q. So when we go into isoquants and isocosts, we're going to only take 2 possible inputs, x1 and x2. We're going to think about all the production being made out of 2 different inputs, because we can graph things in a 2-dimensional space. Sometimes we think about it as the one input that we're trying to study, like pollution or clean air, and all other inputs bundled together into the x2. I'll talk about this later, but yes, this could be like air quality or water quality, and this could be all other inputs if we were studying pollution. So like we did with the budget constraint, we're going to look at combinations of these inputs, little bundles of these inputs, and we're going to call that a technique. A technique is going to be a bundle of 2 levels of 2 different inputs that we're going to combine together. That's going to result in an output Q. We're going to say there's a technology underlying it, and the technology is the way at which the two inputs can be transformed into the output Q. So here's my just sample here. We have apple crisp. We can take a bag of apples, a stick of butter, a cup of brown sugar, which is probably a lot, a cup of oats, a cup of flour, some oven time, some of my time to mix it up. And so these are units of inputs that we're putting in. We can vary those inputs, have a little bit, get different. We'll still get an apple crisp out, but we'll vary things a little bit. My kid made the apple crisp this week, and he decided that it should be ginger instead of cinnamon. It was really good. So the family recipe has changed. Importantly, we'll come back to this, short-term versus long-term, but the dimension of time matters a lot in how we think about this. So I just want to motivate this at the beginning, and we'll talk about it later when we have long-run cost curves and short-run cost curves. But right in the short term, we'll think about we have some fixed inputs and some variable inputs. In the short term, we're only able to change the variable inputs. In the longer term, we can change all of the inputs. So when we do cost curves, we'll do short-term and long-term cost curves The very long term is something where we say the technology itself can change. The technology that transforms these inputs actually changes. A lot of times, the very econ one is to say that quantity is a production function of capital and labor. We would say in the short term, capital is fixed, but labor is variable. So in the short term, we can vary the amount of labor involved, but we can't change the size of the factory. In the long term, we can change the amount of capital that we have. We can add production to our factory. And in the very long term, we can have technology change, and the actual function itself can change. These are just abstractions, but classic ones. So here we have efficiency. So we have two bundles or techniques, and we want to be at the most efficient point. We would say if these two bundles are going to produce the same amount of output, then the outer bundle is inefficient. If these two are producing the same amount of output, this Z1 bundle has more of input 2, it has more of input 1. It's inefficient. The more efficient point to produce would be down here. So mathematically, you could also say that the Z1 was here or the Z1 was here, and that way it just has less of one input or the other input and still would be less efficient. If we get to points that are along here, then we're not quite so sure. But if it's producing the same amount of output Q and has more of any one input, then it's not efficient. We want to produce the output Q with the least amount of inputs. So this is motivating what we call the isoquant. So we're going to say an isoquant is a certain amount of output. And an isoquant is going to be a map, a graph, a curve of all of the different combinations of inputs that can produce that Q star that we've picked, a certain amount of output. The Greek behind the word, iso meaning same, quant meaning same quantity. All the different efficient combinations that produce the same quantity. Here's just a motivating one. Corn is produced with two big chemical inputs, nitrogen and phosphorus. We'll come back to this. We'll talk about this. I think I showed you the dead zone in the Gulf of Mexico from too much of these. But anyways, we can think about there being isoquants in here. So maybe this one, and then, so these numbers here are yield of corn. And these numbers here are how much nitrogen you put on an acre, and this is how much phosphorus you put on an acre. So if we see there's 102 and 102 are here. The same amount, the same quantity has been produced with different input bundles. So we could go maybe something like this. Here's another isoquant. Here's another isoquant. 114 has been produced with these two different sets of inputs. The x1 and x2 are changed, but you're getting the same output.
Sorry, can you say what an isoquant is again? It just went to...
It's all the efficient combinations that lead to a certain level of output. So here we'll say that, somewhere between 105 and 110 is a Q star. And there's 1, 2, 3, 4 different bundles of inputs added to the land that will get us to that bundle. The farmer could be deciding between 200 nitrogen or 80 nitrogen and 40 phosphorus and 80 nitrogen and 160 phosphorus, and we'll get to this based on what the relative prices of nitrogen and phosphorus are. Do they want to be over here or do they want to be over here is a question of the underlying cost of those inputs. But in terms of how much they're going to harvest with these very different ratios of nitrogen and phosphorus, they're going to get the same amount. This is going to look an awful lot like the indifference curves that we've actually done. We're going to think about this in terms of trade-offs, which we want to do all the way through. From the beginning, we want to think about economics and trade-offs, and toward the very end, we're going to think about trade-offs. Here, we're going to have trade-offs between these two factors of production, between the nitrogen and the phosphorus. We're going to try and balance this trade-off in a way that costs us the least. So we have our isoquant, the combination of inputs that produces the given output, and then we're also going to have isocost. The isoquant, when we did it in demand, was like the indifference curve. And the isocost in demand was like the budget constraint. The isocost is going to have all of the different combinations of inputs that cost a certain amount. The price of each input times the quantity of the input summed up is going to be the cost. So in any isocost line, it'll be the same total cost changing. So isoquants we are going to propose have this moon shape here. Let's say they're nested. I talked a lot about maps and topographic lines. They can't cross. As you go up, these would represent different quantities. And so these would represent increasing quantities of output. Along a given line, we would have different bundles. I'm just throwing a couple bundles in here. We can label them A, B, and C. Along a given line, the quantity produced at A is going to equal the quantity produced at B, is going to equal the quantity produced at C. So these are different amounts. Oh yeah, always got to label your axes. It's important to think about the axes. They think about what sort of space we're in. So this has just the quantities of the inputs on it. There's not really prices yet. It just has how much of each input we have along each. And if we read off where part A was, let's say we have 10 units of x2 and 25 units of x1. Each A, B, and C would be different bundles. So let's say this one is 15 and 17. This one is 10. So this out here would be 30 and 10. These are each sets of inputs that produce the same level of output. I know this is kind of slow motion, but I just want to make sure it gets through. Another thing we could think about just while we're at motivating the isoquants is if the technology does change. This is the very long term. So once again, if we had 3 of them, and we started producing up here, and then in the longer term we got to the next, and we got to the next, this would be technological change if the quantity was equal. We would say the amount of inputs it takes to yield a same unit of output is going down, so we would say the productivity is going up. Technology underlying the production function is changing. If we have point A, we have point B, we have point C. We have the amount of inputs in these bundles is less to produce the same level of output. So we have decreased the amount of inputs, but we're getting the same level of output. We won't talk about this as much, but I just wanted to motivate it while we were here. Yeah?
I'm a little confused on why Q01 is worth it. They're different.
Right. So the rest of the time will be in this world, where that quantity is increasing. I just wanted to motivate a certain case where in a longer-term process, the technology underlying the production function could get more efficient, and other aspects of how the transformation of inputs into outputs got more efficient. So in that specific case, less inputs would lead you to have the same output. But most of the time, we're going to be in a space where higher would be higher quantities. So maybe that technological change was a distraction. Stick with your intuition that higher would be higher quantities. So let's think about this. What does it mean to be in a two-input world? As I said before, an econ 1 would be Q equals F of capital and labor. This is a classic production function. You have machinery and workers. How do you get the input combination that's the right amount of spinning looms and industrial workers? That's the Industrial Revolution. They used to have a lot of workers. Over time, they invested in, got more and more machinery and less workers. Productivity is changing. We had the early example of we had bus tours going to Yosemite. We would have buses and the drivers in the bus. We have a bus company. The example that we'll go through in Chapter 8 is we are growing lettuce in the Salinas Valley. And there are two main inputs affecting the yield of lettuce that are how much water we put on each acre of land and how much nitrogen we put on each acre of land. So obviously there's many other things that go into lettuce production, but we're trying to analyze, I'll talk about this later, but we're trying to analyze the water pollution from nitrogen. So we want to isolate it into these two variables that we think are driving pollution. So we hold other things constant in the production function. We just focus on these two. The classic econ 1 question is you have labor and you have other variable inputs. Say you have hired one baker to run your bakery. How much flour do you want to buy? How much can they produce in one night? So true world production has an awful lot of inputs. We need to drive things down into two inputs so that we can model it and sort of simplify it and understand it. So let's think about what points are efficient or inefficient. So if we want to be on the isoquant Q1, point A and point B are both efficient points to produce. We are in the indifference curve question, we would be indifferent between producing, or these would produce the same amount in the isoquant question. Point C has more of this input than A or more of this input than B, and it would be an inefficient way to produce Q1. Point A and point B are equally efficient. They're both on the efficient frontier, and C is not efficient. It would cost us much more than it's going to yield. So we now motivate a cost line. The way we think about a cost line is, let's see if I got the notes for this one. The way we motivate, let's see, is it over here? No. OK, the way we motivate a cost line is we have, now I'm going to, instead of x1 and x2, now we'll do water and nitrogen, because we're now in Chapter 8. So this graph will now match up with the Chapter 8 graphs. This is the total cost to produce lettuce will be the price of nitrogen times the quantity of nitrogen plus the price of water times the quantity of water. And if we want to graph this in this space, we could solve this for water. And this would be total cost over the price of water minus price of nitrogen divided by the price of water times nitrogen. So once again, two input, two variable world, we'll have two terms here. This term will be an intercept, and this term will be a slope. Our intercept term in difference curves and budget constraints was what if we spent all the money in our pocket on donuts? Now we're saying what if we just applied water and we spent all the money on water? Total cost divided by the price of water will give us an intercept. Total cost over the price of water. And then there'll be a line with a slope. This slope here will be minus the price of nitrogen over the price of water. And we would also know where this intercept would be. This would be total cost over the price of nitrogen. So that's what I just did. It's the minimum amount that we would need to expend to produce Q star, some level of production that we've chosen. Here we have a term, the marginal rate of technical substitution. This is a very big mouthful. You can also, in an Econ 1 textbook, it will be called the MRTS. But this is important because behind all this, we have calculus, and we have what's a marginal analysis, sort of behind it all. We always want to think